evaluate a challenging integral. Consider y equals the inverse sine of x. The negative 1 is not an exponent. It denotes the inverse function. Note that y equals the inverse sine of x is equivalent to x equals sine y. That is, y is the angle whose sine is the number x. The domain is when x is between negative 1 and 1. When x equals a half, for example, y equals pi over 6, since sine of pi over 6 equals a half. Since there are infinitely many angles, y, satisfying sine y equals a half, we must select a unique value for y for any given x. We will now restrict y to negative pi over 2 to pi over 2. To differentiate y equals the inverse sine of x, write x equals sine y and take the derivative of both sides with respect to x, using implicit differentiation, getting 1 equals cos y times y prime. Since cos y equals the square root of 1 minus sine squared of y, which equals the square root of 1 minus x squared, we get 1 equals the square root of 1 minus x squared times y prime, or y prime equals 1 over the square root of 1 minus x squared. A beautiful intended consequence is the integral of dx over the square root of 1 minus x squared equals the inverse sine of x plus c. To find y prime if y equals the inverse sine of 2x squared, we use the chain rule to get y prime equals 1 over the square root of 1 minus 2x squared times 4x, which equals 4x over the square root of 1 minus 4x to the fourth. We evaluate the integral of dx over the square root of 1 minus x squared from 0 to a half. Here goes. The integral of dx over the square root of 1 minus x squared from 0 to a half equals the inverse sine of x from 0 to a half, which equals the inverse sine of a half minus the inverse sine of 0, which equals pi over 6 minus 0, which